All right, lesson 2.3, continuity and the intermediate value theorem. Let's get right to it. We got a lot to cover, but I'm hoping to be able to do it pretty efficiently. First, I normally start up with a warm-up with kids just to remind what a continuous function is. Reminder, a continuous function is exactly what it sounds like. It's something that's continuous, right? No breaks in the graph. If you had something that was not continuous, if you had some function that was not continuous, then all you have to do is put some kind of break in the graph. There's lots of different breaks in the graph I could make, and that's what today's lesson is going to be about. When you put a break in the graph, it's called a discontinuity. So there's ones, let's see here, I'm going to change color quick. I could have a discontinuity like that. All right, that's called a hole, or a removable discontinuity. But there's a break in the graph, right? There's a little part where there was a break where it didn't continue. It wasn't continuous. I could do one like this, where you have that kind of asymptote. That's called an infinite discontinuity because it goes up towards infinity. I could do one like this. Maybe it starts here, stops, and all of a sudden picks up again up there. That's a discontinuity. That's called a jump discontinuity. So today's lesson is going to be talking about these types of discontinuities: removable, also known as a hole, infinite, and jump. And then we're going to talk about something called the intermediate value theorem, which will be coming up in a bit. All right. So first, just being continuous. Sometimes people are thrown off when they're asked, like, is it continuous at a certain point, right? Like, is this function continuous at the point x equals 1? Well, here at 1, I'm right there. So like the question is, am I continuous at that point or not? What about at the point x equals 2? Right there, is that continuous? What about x equals 3? Right there, is that continuous? And when we're talking about the insides of a function, like we're going to talk about them separately than the endpoint. So let's ignore this point and this point for now, because those are endpoints and they're a little different. When we think about continuous, if I look at the point x equals 1, that's happening right here. Let's change the color. For x equals 1, that happens right here. That's definitely not continuous. There's a jump discontinuity right there, right? So it's not continuous at x equals 1. No. When I look at x equals 2, that's right here. That's another jump discontinuity. It's traveling along, jumps up to here, jumps back down, travels along more. That is not continuous at 2. However, at the point x equals 3, I am continuous at x equals 3 because on the left side, I'm going towards that point. I hit that point. And on the right side, I keep going. So you're continuous if you're approaching that same location from the left and the right and you hit it, right? It's just continuous. There isn't any break in the graph. So a formal way to define continuity is if the limit as you approach some number c is the same as plugging that c in. In other words, the function of f of x is continuous at an interior point, we're ignoring the endpoints for now, if and only if the limit as x approaches c of f of x is the exact same thing as f of c. So in this example here, we were continuous at x equals 3 because the limit was approaching this value right there, which is a value of 2. And if I plugged a 3 in, I got a 2 out. It was the same for both of those. That's why that at x equals 3, that was the only point that was actually a point where I was continuous at that point. If you want it written down, there you go. The limit of f of x as x approaches 3, right? The limit was going towards that point, which has a value of 2. And also, f of 3, plugging that 3 in, gets me a 2 out. If that happens, you're continuous at that point. All right. The endpoints are a little bit different. The endpoint, since there isn't anything over here to consider, we're not going to consider the limit as a whole. We're just going to consider the one-sided limit. And so it's the same definition. It's just looking at the one-sided limit. If the one-sided limit is the same as plugging it in, then you're continuous. If the one-sided limit is not the same as plugging it in, then you're not continuous. So if I look at this point at x equals 0, if this one on the left right here, if I tried to find the limit from just the one side, so in this case from the right, so limit as x approaches 0 from the right side, I'm going going towards that value there, which is a value of 1. If I try plugging a 0 in, I can. F of 0, I land right at that point. That's 1. The limit is the same as plugging the number in. Yes, you're continuous at 0. However, if I look at point 4 over here, though the limit exists, the limit is going towards 1. If I tried plugging a 4 in, I can't do it because there's a hole there. There's nothing I'd get out. And you'd say the limit as x approaches 0, sorry, as x approaches 4 from the left, that reset exists. It's going towards that hole, which has a value of 1. But if I tried to plug in f of 4, I ended up at a hole that doesn't exist. These are not the same things, obviously, so we're not continuous at 4. That was pretty fast, but I'm hoping it made sense to you guys. All right. Intervals over which a function is continuous. That just means if you can look at a function, what intervals is it continuous over, right? So we've already mentioned we found where it's not continuous. We're not continuous here at 1. We said that was a jump discontinuity. We're not continuous here at 2. That is also a jump discontinuity. We're not continuous here at 4. That's where we're not continuous, which means we're continuous everywhere else, right? So I am continuous during this entire section here. Not there though. So that would be from here on to there. So I'm continuous over the interval from 0, including 0, because remember we said that endpoint was continuous, on up to 1, but not including 1, because there's our first problem. Union, all right, I'm continuous during this entire section up until that problem at 2. So that's from 1 to 2, not including either, so 1 to 2. Union, then I'm continuous during this entire section all the way up until 4. So starting at 2, ending at 4, from 2 to 4. Not including either, because I'm not continuous here because of the jump discontinuity, not continuous there at the endpoint. We talked about that before. So those would be the intervals over which I'm continuous. So just an infinite set of points, listing them as intervals out. All right, let's get to the meat of this argument. Types of discontinuity. There's really only maybe 3 you really need to worry about: removable, jump, and infinite. There is a cool one called oscillating discontinuities. I don't recall them ever showing up on the AP exam. I will probably talk about them at some point really quickly. You could also Google it. But these are the 3 real big ones: removable, jump, and infinite. So removable, we mentioned before, looks like this. It's also called a hole, AKA hole. So it's called a removable function discontinuity because even though it's not continuous, I could really easily fix it by adding a point to the function. I can say, hey, let's fill that in. Now it's continuous, right? Sometimes they're just blank like this one. Another example of a removable one would be, let me draw a line like this. Traveling along, have that same hole, but then there's a point here, right? So that's defined everywhere, but that point up, oh, I wonder if you can see that. I'm hoping you can. I'm gonna move that point maybe. I'm gonna move the point down here so it's see it. So it's defined everywhere, right? You can put any point in. You can put this value in there. You just land there, but that's still, it's not a jump discontinuity, even though I've mentioned before, you jump down, jump back up. I might have misnamed the other one as a jump discontinuity. If I did, I apologize. That's actually a removable discontinuity. It's removable because I can fix it really easily. I can say, hey, this one point here where I jumped to that point, let's get rid of that, and let's put it right here. And then all of a sudden, I got a continuous function again. So removable discontinuities are discontinuities that you can easily fix and make them continuous. A jump discontinuity is not removable. It's called a non-removable discontinuity. It's where you travel along, you stop at one point, and you suddenly jump to another location. That is not easily fixable because I can't drag this down and make it continuous without changing a whole bunch of points, right? I can't suddenly I'd have to change an infinite number of points to suddenly make it continuous. So I can't really easily fix that. So we just call it a jump discontinuity, and it's also sometimes known as non-removable. Non-removable because I can't really fix it. Infinite discontinuities are also non-removable. We mentioned that that's when you have a discontinuity that's going up towards infinity or sometimes down towards negative infinity. It's not really a jump because it's, well, it's kind of a jump, but I just keep going up and up and up, close more and more towards infinity, never really get there. So that's an infinite discontinuity. It is also non-removable because also there's not a great way to fix it. All right, oscillating discontinuities. They're also non-removable. They're kind of cool looking ones. One good example is sine of 1 over x. If you graphed it, oscillating functions are functions that go up and down, so sine would be an oscillating function. If I tried to graph this one in particular, it would go up and down, but the waves would be slow at first, and then the closer I get to 0, the faster these waves would go up and down. They just get crunched. And by the time you get to 0, they're going up and down infinitely fast. And you'll notice if you look at this equation, you can't actually plug a 0 in. If you tried to plug a 0 into there, you'd have a sine of 1 over 0, which is undefined. So you can't plug 0 into the function. But when you graph it, you get some weird picture like that, where those up and down curves go just crazy faster and faster up and down. And that discontinuity there in the center is called oscillating, because it's basically taking those waves and just crunching them to an infinitely dense section of waves. It's kind of a cool little function. All right. Normally here I do a quick few examples, and I do a sketch and say, hey, name the discontinuity. We'll do that now. It'll be a good practice for you. I'll do a sketch, you name it, I'll confirm it. If you want to skip this part, go ahead. If you feel you got them. Let's do a few quick ones if you don't, or if you want to check it. All right, name that one. It's removable, also known as a hole. Name that one. Still removable. You can change this position, put it in there, it's removable. Name this one. Infinite, going towards infinity. Name this one. It's a jump discontinuity. Clearly making a jump, can't fix it. Oh, let's do a crazy one. This one, people always ask, what about this? I'll name it. What about this? This goes like this, and it stops. And then on this side, goes like that. Name that discontinuity. Nah, it's not really a jump because I can't jump to anywhere. Only one side goes to infinity. This type of discontinuity actually has a name. It's called a mixed discontinuity because it's mixed between a jump and an infinite. If you were to give them just a one name, I think infinite would be the name to give it because you can't really complete your jump. So I think you'd be forgiven if you called it an infinite discontinuity, but I believe the actual term is mixed discontinuity. All right. Some terminology on continuity. A function is continuous on an interval if and only if it is continuous at every point on the interval, and a continuous function is one that is continuous at every point in its domain. And then it notes the importance of the word domain, and I've got it written down here why, but I think I want to just show it off to the side. All right, so if I sketched the graph 1 over x looks like this. Now, if I asked you, is that continuous everywhere, from negative infinity to infinity? The clear answer is no, it is not continuous everywhere. There is definitely a discontinuity. Where at? Well, at 0. There's an infinite discontinuity at 0. So I would say this is function. So this function, I should get a smaller pen, hold on. This function is not continuous at x equals 0. There's an infinite discontinuity there. Now, there's a difference between saying, is it continuous out over some range, and is it a continuous function? It is a continuous function. This is a continuous function, which seems against intuition. But the definition of a continuous function is if it's continuous over every point of its domain. And the domain for this function only goes from 0 to infinity and negative infinity to 0, but the domain does not include 0 because I can't plug anything in, right? There's nothing to plug in there. So over every spot where I can plug something in, it's continuous. We don't count the parts that I can't plug anything in on. So that is a continuous function. Now, if I had changed this function a bit, if I had said, hey, I'm going to add a point to this function. Let me get my pen back and make it thicker again. If I had said, I'm going to add this point right here. So now when you travel along this function, you travel like this, like it's going da 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 da, travels here, then it equals there, then it's there. Well, all of a sudden now that point is part of the domain, and now it wouldn't be a continuous function because hey, I'm like, hey, this is part of the domain, and there's definitely a discontinuity there. So it's a continuous function if it's continuous over every part where you can actually plug stuff in. But then if it's a continuous over an interval, if over any given particular interval, it is continuous. So it is not continuous. So here, one more thing. I'll give you some intervals. So is it continuous over the interval from 0 to infinity? You'd say yes, because that's just this section right here, right? It's continuous over that whole section. If I said, is it continuous over the interval from negative infinity to infinity? You'd say no, because you have that discontinuity there, right? So difference between asking continuity over an interval and asking if you have a continuous function. All right, that's what the stuff in red has said. Go ahead and read it if you like. Moving on. All right, some quick examples about continuity. These are actually pulled from your homework. I did that on purpose to kind of give an indication of especially this thing. You'll notice that one's not shaded, that one is. There is a difference between not shaded and shaded. If it's not shaded, that's your book telling you, feel free to use a calculator to help you out. If it is shaded, that's your book telling you like, hey, I'm pretty sure you can figure this out without a calculator. So make sure you pay attention to that. This example says, find the points of discontinuity, identify each type of discontinuity. This one is allowing me to use a calculator. It says, go ahead. Now, I've been doing math for a while, so I know what that's gonna look like. That's gonna look something like this. So if I graphed it on my calculator, it looks something like that. And if I looked at that, I could say, hey, look at that graph. I'm definitely see it's got a point of discontinuity. It's got a point of discontinuity right here. Hold on, pen's not working. There you go, right here at -2. So I'd say to find the points of discontinuity and discontinuous at x equals -2. And then it says identify the type. Well, this one was going up towards infinity, so it's an infinite discontinuity. Again, you could feel free to use your calculator for that because it wasn't shaded. If it is shaded, then it's saying, hey, you could probably figure this out without a calculator. So if I look at this one, I could look at this, 3 minus x. I know that's just a straight line, that's linear. X over 2 plus 1, that's also a straight line, that's linear. But then it's a piecewise function that switches at 2. So I'm like, at 2, it might be continuous if the two lines connect on the same point, or it might not. So there's a few ways to do this. For me, since I'm really only worried about what happens at 2, I would probably just do it by plugging a 2 into here. If I plugged a 2 into there, 3 minus 2 is 1. If I plugged a 2 into here, that'd be 2 over 2 plus 1, that's 2. I can see that from the left side, I'm equal to 1. From the right side, I'm equal to 2. Those aren't the same, so there's clearly going to be a discontinuity, and particularly a jump one. I'm jumping from a value of 1 to a value of 2. If you followed that along and it made sense to you, feel free to do it that way. Others of you might prefer to actually graph it out to take a look at the function. If that's what you like, go ahead. You can do a quick sketch, right? I can sketch this. Everything less than 2, 1, 2, I can sketch. I always start at the 2 because, you know, you can put on a 1.5 or a 1.9 or a 1.99. So what I'm going to do is I'm going to put a 2 in there. 3 minus 2 is 1, and then I just put an open circle. And then everything less than that, if I put a 1 into this function, 3 minus 1 is 2. If I put a 0 into here, 3 minus 0 is 3, and I can see that the function looks like this line, which we mentioned before that it was linear, right? This is a linear with a slope of -1. And I can do the same thing for this thing, starting with that 2. So put a 2 into there. That's 2 over 2 plus 1. That's 1 plus 1. That gives me a value of 2, which is right here. And then if I put a 3 into there, that'd be 3 halves plus 1. That's 1.5 plus 1. That's 2.5, right about there. If I put a 4 in, that'd be 2, right about there. And I can see it looks like this. And then you can say, all right, well, there's the graph of the function. And you can very clearly see it's continuous everywhere except right there. And that's a jump discontinuity. So it's discontinuous at x equals 2. It's a jump discontinuity. All right. Let's wrap this stuff up. Properties of continuous functions. This I'm going to kind of just skim over. It's on page 82 in your textbook. That's why this is here. Page 82 in your textbook. Basically, it's saying the same thing that we've talked about for other things. If you have two continuous functions, their sums are continuous, their differences are continuous, their products are continuous. If you multiply it by some constant, you're still continuous. If you divide them, you're still continuous as long as that denominator is not equal to 0, right? Because you can't ever divide by 0. That gives you something that's undefined. And even if you do composites, like f of g of x, that's going to be continuous. So if you know you've got two functions that are continuous, so are their sums, so their products, so are their differences, so are any combinations of those. The reason that's important is for a problem like this. Y equals sine of x all over x squared plus 2. If I asked you at the beginning, is that thing continuous or not continuous, you might have been like, I don't know. But we can look at each of these individually. Like if I look at sine of x, that's a function I know. Sine of x is definitely continuous. If I look at x squared plus 2, x squared plus 2 is definitely continuous. That's just a parabola that, intersects at 2, right? So then that means their quotient, if I divide them, that must also be continuous as long as the denominator never equals 0. And if I look at that, well, that's always 2 or bigger. It's never going to equal 0, so then I'm not a problem. So I'm like, well, if this is continuous, and that's continuous, and this is bottom's never equal to 0, then that means the sine of x over x squared plus 2 must also be continuous. Extended functions. A function created by incorporating additional values not included in the original function's domain. So here's an example. We had talked about 1 over x before, right? 1 over x, we said looks like this, where there's really nothing in the domain right at 0. But I can make an extended function out of that by adding something else in. So like I could say, hey, here's my extended function. It's a function that looks like 1 over x for everything that's not equal to 0. But when you plug a 0 in, now you're getting something out. You're getting a 0 out. So if I sketch that, I'm like, all right, for everything not equal to 0, it looks like 1 over x. It looks like that. Plus, now I know when you try to plug in a 0 instead of not getting anything, you get a 0 out. So I get that function. That's what the extended function would look like. It's just adding another point into the function so that it's defined everywhere. And there's not a point where, say, plug in 0, what do you get out? And you're like, oh, you don't get anything out. Now I say, plug in 0, what do you get out? You get a 0 out. All right, so extended functions, adding points into the function. Here's an example. Define a piecewise function for the extended function of f of x equals sine of x over x that is continuous at x equals 0. This one I would say would be a calculator allowed. If you tried to graph this, I don't remember perfectly, but I believe it looks something like, you notice it's not continuous at 0 because there's that hole right there. However, I can add a value to make it continuous. If you remember, this is one of the ones I said you probably want to memorize. That's limit as you go towards 0 is 1. So that hole is happening right at the value of 1. So if I wanted to fill that in, I need just to put a point right there. And then all of a sudden it's continuous. And you could be like, da, 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 da. Oh, there's not a hole anymore. It's filled in. And you can keep going, right? So we're just going to define that function so that we can go. So that function, use my little squiggly to show it's a piecewise defined function. We're going to call it f of x, and it's going to be the same thing just about everywhere. It's going to be equal to sine of x. Sorry, equals. It's going to equal sine of x over x whenever x is not equal to 0. But then when x is equal to 0, I want to get this value out right there. I want to fill that hole in. So I'm going to make it equal to a value of 1. Extended function that is now making that sine of x over x continuous. All right. I'm going to end it here. I'm going to make a separate video for intermediate value theorem so that if you want to take a break, absorb some of that material, it's a good time. If you want to prep for it, the homework, like if you want to get some homework in first, all of the homework is essentially on what we just talked about. There's just going to be one problem that's on the intermediate value theorem, mostly because the book didn't do a great job with providing examples that are good intermediate value theorem examples. So I took one from an actual AP website that's more of like an AP type of problem for intermediate value theorem. Intermediate value theorem is important, but it's something that I'm going to say, let's watch in a separate video. All right, bye-bye.